All right, in this video, we are going to move to the end of chapter 2 and cover the last two sections of material that we need for this class. So for the first time, and we'll see this a few more times in other videos, I'm going to do what I call a combo section, where I'm going to do two sections in one video, because I don't think it makes a lot of sense to split these up and have to do two very small videos. These topics go so well together that we might as well do it all at one time. So we're going to do sections 2.8 and 2.9, where 2.8 talks about subspaces of the nth dimension. And then in 2.9, we'll get into more of the idea of what dimension and rank are when it comes to matrices. So a little bit of talking here at the beginnings. We got some new definitions we want to go over, with the big one being subspace. So for the next little bit in this video, we're going to talk about what a subspace of a certain dimension is. So as you can see in my definitions up there, a subspace of the nth dimension is any set H that exists in that nth dimension that has the following properties. So we've got three properties here that we want to check. Number one, is the zero vector in this set H? So that's criteria number one. Criteria number two, for any two vectors that exist in this set H, when you add them together and get u plus v, this should also be in that set H. And finally, excuse me, I got the hiccups here. For any vector u, just one of them, that's in H, if you multiply that vector u by any scalar c, then the vector c times u needs to also be in the set H. If all three of those criteria are met, then we can say that H is a subspace of the nth dimension. So to kind of show you a visual representation of what this is, I tried to put a picture over here to show this. This is kind of the idea that goes into verifying that something is a subspace. So let's assume, for example, that we have two vectors, v1 and v2, that we know are both in the same dimension, Rn. Let's define, let me get my highlighter out here. Let's define our set H as being the span of those two vectors. Now, if you recall, when you span two vectors back in chapter 1, it creates this plane-like or this parallelogram idea that expands over an entire dimension. The visual I have here is a third dimension, but it applies to any dimension of these vectors existing. So what I'm about to show you is, why is H a subspace of the nth dimension? So what goes into us verifying that? Well, as you can see, to verify, note that the zero vector is in H, because what we know is if I take 0 times v1 plus 0 times v2, which is a linear combination, which is the definition of spanning, all right, that's got to be in the span. So all you got to do is let your two constants be 0, and that's going to create the zero vector. So that one's pretty nice. So now moving to criteria B, how do I show that the sum of the two vectors is in the span as well, or in this set? So if I take two arbitrary vectors in H, so let's say that, let's let vector u be a1 v1 plus a2 v2, and let's let v be b1 v1 plus b2 v2. So two different linear combinations. So remember, both of these u and v have to be the span of v1 and v2. Well, if I were to do a little bit of arithmetic here, and I didn't show every step in my notes, but we can kind of visually see this. If I were to add the u and v that I have listed here, I could group the v1 pieces together and the v2 pieces together and get the following, where you would have a1 plus b1 as your new constant of v1 plus a2 plus b2 as your new constant of v2. And as you can see, since these are just different constants, this falls into the definition of what the span of v1 and v2 is. As long as each of those has a constant, that falls into a linear combination. All right, and hence is in the subspace, or in, I guess we're calling it the set for right now. And then last but not least, for your last criteria, or criteria C, if I take any scalar C that exists and I multiply it by, let's just say, the same vector u, well, c times u would equal C times the A1 V1 plus A2 V2. And if I purposely group things in a different way, so I'm distributing this C to both terms and regrouping my constants. So my new constants become CA1 and CA2. Once again, those are still constants that are being multiplied by the vector V1 and V2. So that also falls into the criteria of the span of V1 and V2. All right, sorry about that. My mother called me and I had to answer because she never calls me, and sometimes that usually means an emergency, but all good. But very good. That's kind of how we verify things are subspaces here. All right. So one thing to keep in mind is that this is not a theory-based class. If you were to take one of our theoretical linear algebra classes that we offer at Mississippi State, you would do this a lot more, where you have to prove things are subspaces in different regards. This is more of an applied linear algebra class, so I'm never going to make you verify something as a subspace, but what I am going to do is that when I claim something is a subspace, just know that all this stuff would check out. Now, for this particular class, there are certain subspaces that we want to put our attention on that we can actually do applied-wise and find them. So the two that we're going to see and talk about today, in the first little part, the first one is called a column space. So the column space of a matrix A is the set that we're going to denote from this point forward. Column space is COL of A. Just know that that's what it means going forward. And what it means to y'all is that it is all the linear combinations of the columns of A. So now keep in mind that is infinitely many different combinations, because if you let the constants be any set of, or pair of numbers, that would fall into the column space of A. Now, just because there are infinitely many of them does not mean every single pair of vectors or every vector is in the column space. There's just a whole bunch of them. So a little note here that I put for y'all just for reference purposes is that if we assume that A is an m by n matrix, then when you find the column space of A, it will be a subspace of the nth dimension, which if you keep in mind what m is, which is the first number of your dimension, that represents the number of rows in your matrix. So thinking about this way, when you find the column space of A, which I'll show you how to do in just a minute, you will have whatever the number of rows are in the original matrix A, that will tell you the dimension that you're focusing on when it comes to column space. The second type of subspace that we're going to work on is called the null space. So the null space of a matrix A is denoted as NUL of A. So that's how we'll note null space going forward. What this is defined as is it's all the solutions of the homogeneous matrix equation AX equals 0. So we talked about that back in chapter 1. We're about to show you in this video how that relates and becomes a subspace. Well, think a little backwards here on the next part. If A is once again an m by n matrix, then the null space is going to be a subspace of the nth dimension, which once again, going back to how it's denoted, that denotes the number of columns that are in the original matrix A. So number of rows represents the subspace dimension of your column space. The number of columns represents the dimensional subspace that's going to be the null space here. All right, so now that we know the basic definitions of column and null space, let's do kind of a little bit of an example where I'm not going to make you find the subspaces just yet, but I want you to be able to verify if a certain vector falls in that subspace. So here's my example to illustrate that. If I give you three vectors, let's say V1 is 1, -4, -3, V2 is -3, 6, 7, and V3 is -4, -2, 6, and let's let vector P be 3, 3, -4. Sorry again for that. I guess today's the day that everybody wants to call me when no one ever calls me on my cell phone. So hopefully that's the end of that after that conversation. So like I said, I was reading out the vectors we have here, and what I want to do is I want to show you not how so much to find, the column in null space just yet. We'll get into that. But how do you verify if one particular vector exists in either one of those? So on part A, it says determine whether P is in the column space of A, where A is the matrix defined as the columns V1, V2, and V3. So for something to be in the column space, it means that the vector has to be a linear combination of the vectors that are in that matrix. So for part A, all you have to do to verify that a vector is in the column space is we are going to take the 3 vectors that they give us, and we are going to augment those with whatever vector you're checking, which in this case is the 3, 3, negative 4. Now, we don't care what the answer to this augmented matrix is. The question is it a solution? Can P be a linear combination? So you just got to verify that as long as it's consistent, you're good to go. So my thought is let's put this in echelon form, and that should be enough for us to solve this. So to do that, I'm going to take row 2 and add 4 row 1s, and I'm going to take row 3 and add 3 row 1s. So your top row will remain the same. Your middle row is going to be 0. That's going to be 6 minus 12, which is negative 6. Negative 2 minus 16 is negative 18. And 3 plus 12 is 15. And then the bottom row, we're going to add 3 row 1s. So that would be 0. 7 minus 9 is negative 2. 6 minus 12 is negative 6. And then negative 4 plus 9 is going to be 5. And so what some people notice is that row 2 and row 3, you could scale those a bit, but I'm actually not even going to do that in this case. Instead, what I'm going to do is I'm going to notice that row 2 and row 3 are actually multiples of each other. If you notice, if you take every number in row 2 and divide them all by 3, you get the numbers that are right below it. And so remember, when 2 rows are multiples of each other, the bottommost row goes to all zeros. And then everything else will remain the same. And at this point, I think we know enough to answer this question. Because if you look at, remember back from chapter 1, if you look at the pivot positions, you have a pivot position for x1, you have a pivot position for x2, and then in the x3 pivot position, you don't have anything, but that's okay because you have a row of all zeros. What that tells us is that x3 is a free variable, which implies that the matrix is consistent, which implies that the answer to this question on part A is yes. P is in the column space of A because it is a linear combination of V1, V2, and V3. Now, for part B, a little bit different question. It asks, is P in the null space of A? So to verify that, remember for null space from the last slide, is it a solution to the homogeneous matrix equation? So in this case, since this is the homogeneous matrix equation, we just need to replace X with whatever vector we're trying to verify. In this case, that would be P. So the question you're trying to answer here is A times P equal to the 0 vector? So to do that, we're going to take matrix A, which remember A is the 3 vectors V1, V2, V3. And we're going to multiply that by P, which is 3, 3, negative 4. And you're going to multiply these using the row column rule. So remember the rows of the first times the columns of the second. So if I take the first row of the matrix and multiply it by the elements of the column and add them all together, that would be 3 minus 9 is going to be negative 6, and then negative 6 plus 16 is 10. In this case, I actually could stop right there. I already know that this is not going to equal the 0 vector because the first element is not 0. But just for those who want the practice, I'm going to go through and take the next two rows, multiply them by the column, and see what number you can get so you can practice this as well. So if I take row 2 times the column, that would be negative 12 plus 18 is 6, and 6 plus 8 is 14. And then the third row times the same column, that would be negative 9 plus 21, which is 12, and then 12 minus 24 is negative 12. Anyways, this is not the zero vector, so when the question becomes, is P in the null space of A? The answer is no, because it does not solve the homogeneous matrix equation. All right. Now, one of the problems with these subspaces that we're about to get into how to find these on your own. You can't find every single vector in a subspace because there are infinitely many. So what I'm going to instead have us do is we're going to find what's called the basis of a subspace. So let's go over what that is first. A basis for a subspace, and I'm just going to keep using H for right now, is going to be a linearly independent set in H that spans H. So instead of finding every vector in this subspace, can we find a set that's just a finite number of vectors that would be linearly independent and spans the entire subspace H you're trying to work with? Now, as far as a homework question goes, please be careful. A basis is defined as a set of vectors, which means you must enclose your vectors in curly braces to represent the set. And we'll see that in a few minutes in our example. And you'll actually see it here at the bottom as well. So here's how you find the first one. We'll start with column space. Easiest one of the two. The pivot columns of a matrix A make up the basis for the column space. All right. So all you have to do is find the pivot columns. You may recall back in chapter 1, we talked about pivot columns at that point, but I didn't really focus on them too much because they weren't needed. Now they're needed to find the basis of a column space. So for example, just one problem I made up and we'll do it really quickly. Here's your matrix A, 3 by 3, 1, 3, 5, 1, negative 1, 1, negative 3, 2, negative 4. I am claiming that the basis for the column space are the two vectors mentioned here. This is completely based on the echelon form of A. So what I'm going to do is if I take that matrix A, if I wanted to put it in echelon form, I would take row 2 and subtract row 1, and I would take row 3 and add 3 row 1s. 1, 3, 5, you would get 0, negative 4, negative 4, and then you would get 0, 2 plus 9 is 11, negative 4 plus 15 is also 11. And then I notice that row 2 and row 3 are multiples of each other. So I can make the bottommost row all zeros. And at this point, that's enough to find my pivot positions. Now you'll see that by the end of this problem, I found the pivot positions to be in column 1, or let me call it the X column 1, and column 2. So remember, pivot columns come and go back to the original matrix A. So if I go back to the original matrix A and identify the X1 and X2 column, that is the two columns that I am writing in my basis. So I wrote open curly brace. I wrote the first column as a vector. I wrote the second column as a vector, and I closed my curly brace with a comma in between them. This would be how you find the basis of a column space. Then we get into the basis of a null space. Once again, there are infinitely many vectors in this subspace, so we don't want to find them all. Instead, we just want to find the ones that make up a linearly independent set. So to do that, the basis for a null space of A is obtained from the parametric vector form of the homogeneous matrix equation. So if you go back in your notes, if you need to, or go back and watch the video, in section 1.5, we learned how to find a parametric vector form of a homogeneous matrix equation. If you remember, your answers will be in the following form. Vector x is x1 u1 plus x2 u2 plus et cetera, all right? Each of those is represented as free variables. So whenever you find a free variable, that tells you how many vectors you'll be adding together in your parametric vector form. So what we want to do is to find the basis of the null space. The only part you need is you will take the vector u's off of your parametric vector form and make that the basis of your null space. For example, just so you can kind of see what we're going to be doing, and I'm going to make some really, really easy numbers up here. If this ends up being your parametric vector form where you have x2 and x3 are free variables, and you're going to have this form. If you want to make this the basis of a null space, you would take just the vector part. So 1, 2, 3, and then 4, 5, 6, and write those in your basis. There's no need to bring over the x2 and x3 because that is not needed. All right. So now that we know how to write these answers in this form now, we are going to do our first example of how you find the basis of each one. So this can be a little bit time consuming. So what I will typically do is try to make your life a little bit easier, and I will do part of the work for you, and then I want you to fill in the rest of it. So matrix A and the echelon form of that matrix are given below. I want you to find a basis for the column space and a basis for the null space. Right? So to do that, you'll notice that we have our matrix A, and then right here is the echelon form. I always begin with the basis of the column space of A because you only need echelon form to do that. When I look at the echelon form of my matrix, I notice that I've got two pivot positions in the x1 and the x3 column. So if I go back to the original matrix and I identify the two original columns that match up, that's what I'm going to write for my basis. I'll go squiggle brace. I'll do the first vector, which is 3, 2, 3, comma the third vector, which is 9, 7, 6. This is the basis of my column space. It's always the easier of the two. To do the basis of the null space, you're going to have to do a little bit more work because you're going to have to get all the way to reduced echelon form to do that. So remember, we need to solve the homogeneous matrix equation to do this. So I'm going to take the echelon form of my matrix. Let me get that written down here. And then I'm going to stick a column of zeros to make it augmented and thus also homogeneous. To put this into reduced echelon form, it looks like you just have to do one step here. You got to get rid of that 3 above the second pivot position. So I'm going to take row 1 and I'm going to subtract 3 row 2s. It doesn't change much because you're going to have 1, -2, 0. The number that it changes is that next one because you'll have 0 minus 6, which is -6. And I don't believe anything else in this problem changes. Now that you have reduced echelon form, remember you can take this and write out what it says. This says that x1 minus 2x2 minus 6x4 is 0. The second row says that x3 plus 2x4 is 0. And then going off the columns you didn't circle, x2 and x4 must both be free variables. Now you need to solve for the basic variables here. Remember, that's the pivot positions that you circled. So coming down to the next line, we would say that x1 is equal to 2x2 plus 6x4. We would say x3 is negative 2x4, with x2 and x4 still being free. Right? So from here, we can say that vector x is going to equal your first free variable x2 times a certain vector plus x4 times another vector. Remember, you pull those from the coefficients of your basic variable equation. So for x2, you would have 2 in the first position. When the position matches the free variable, it would be 1. There's nothing in the x3 equation that helps you. And then when you get to the other free variable that doesn't match, you put a 0 by default. For x4, following the same pattern, you should get 6, 0, -2, and then 1 when it matches. This is your parametric vector form, but to write it as the basis of the null space of A, we would write this as curly brace. You would just pull the 2 vectors off that you found. So 2, 1, 0, 0, and 6, 0, -2, 1. This is the basis of your null space, and that's how you find the basis of your column and null space as well. Right? So now that we've talked about the basis idea, we want to move into the last little bit. So we're kind of moving into the 2.9 stuff that we were doing, and that was talking about the dimension part. So now that we've found the subspaces, we want to talk about what the dimension is and how you go about finding that. So new definition here. The dimension of a non-zero subspace H denoted by, and here's our new notation, we got a lot of that today. When we write dim of H, that denotes dimension. All this is, it is the number of vectors in any basis for H. So once you find the basis of a subspace, you count the number of vectors in there, and that is what your value will be. These will just be constant answers that you're going to find. So just for something we might run into later, and we may not, but just in case we do, if you ever get a subspace that is just the 0 vector, we do not count the 0 vector in our dimension. This is defined to just be 0. So do not include the 0 vector when you're counting if that's the case. All right, so how do you find the dimension of the 2 subspaces we just talked about? The first one, the dimension of the column space. That's the one that actually has a fancy name for it that you can use. Another way to denote this is that some professors and some teachers prefer to call this the rank of A. So the rank of a matrix and the dimension of the column space, these are interchangeable words. All right. If you're a person who wants to use the rank notation, it's just written as rank of A. You can write it that way. It doesn't matter to me. What this will be is this is the number of basis vectors in the column space of matrix A. And a surefire way to know whether or not you got the right number is that this should always match the number of pivot columns in A. That can also be the number of pivot positions. So however many pivot positions / columns you get, that should be the number you're using for rank of A. Versus when we do the dimension of the null space of A, there is no fancy name for this, so don't look for one. Instead, this is just the number of basis vectors in the null space of A, which if you're looking for a way to check your answer, it should be the number of free variables that you find in your homogeneous matrix equation. So once you find both of those, another thing that you can do to kind of double check your work, there's a nice little theorem called the rank theorem. And we're going to use this a good bit in the next few videos. The rank theorem, to use this theorem, we are going to let matrix A have n columns. What should always happen is after you find the rank of A and you find the dimension of the null space, when you add those 2 dimensions together, it should always equal the number of columns in the original matrix. So if we go back to the previous example that we just did, When we found the basis of the column space, there were two matrices, or two vectors in that basis. And when we found the basis of the null space, there were two vectors. Obviously, we know that 2 plus 2 is 4. And if you go back to the original problem, there were 4 columns in the original matrix A. That will always be the case, and it's a way we can double check that when we did our row reduction and we did our simplifying, we're getting the right results. All right, so let's do an example of that. All right, so once again, to save us a little bit of effort, I kind of went ahead and did the echelon form for you, and then we will kind of find the extra bit of information. So we have this matrix A, which is a 4 by 5 matrix, and then I have the echelon form right next to you. All right, so actually, I went a little step further. I was a little bit nicer. This is actually the reduced echelon form. So just to save some time, let's find the bases for the column space of A and the null space of A, and then state the dimensions of these subspaces. So beginning with the easier one, we're going to do the basis of the column space of A. So remember, go to your problem and identify your pivot positions. So you got this one, this one, this one, and this one. All right. So you've got 4 pivot positions in the first, second, fourth, and fifth column. So just kind of keeping myself organized, we have to write all 4 of those columns in the original matrix in our basis of the column space. So the first column would be 1, 2, negative 2, 3. The second column would be negative 2, negative 1, 0, 1. We skipped the third column because it did not have a pivot position. Then we have 5, 5, 1, 1. And finally, we have 4, 6, negative 6, 5. Right? So you have just answered the first question. You found the basis of the column space. So now you want to focus on the basis for the null space. So remember that you have to set up a homogeneous matrix equation. Sorry, lost my train of thought there for a second. The good news is we're going to take our matrix A. Remember, go ahead and take that last matrix, the 1, 0, 1, 0, 0, and continued. 0, 1, 1, 0, 0, 0, 0, 0, 1, 0, and then 0, 0, 0, 0, 1. And I'm going to add the column of zeros on the end. Now, unlike the last one where we had to keep reducing it, this one's already in reduced echelon form for you. So we can go right into the steps of solving this. The first row would say that x1 plus x3 is 0. Then we have x2 plus x3 is 0. The third row says that x4 must be 0. And the last row says that x5 must be 0. Solving each of those for the basic variable, which remember that's the 4 pivot positions you found, you should have x1 equals negative x3, x2 equals negative x3, x4 is still 0, x5 is still 0, and that now allows me to write the parametric vector form of our solution. So vector x would be, oh, I forgot to write the free variable. Apologize there. x3 is free, x3 is free. So since there's only one free variable, we will only have one vector in this notation. All right. So for the x3 coefficients, you should get negative 1, 1 because it matches, and then x4 and x5 must both be 0. So to write the basis of the null space of A, this is going to equal squiggle brace, write down the one vector that we just found. Negative 1, 1, 0, 0, and close your brace. That is the basis of your null space. So that's kind of repeating the process of the previous problem. What we're going to add in here is now I want you to tell me the dimension of each of these. So that's pretty easy to do at the end. To find the dimension of the column space of A, which is also known as the rank of A, just count the number of vectors you found. 1, 2, 3, 4. This is equal to 4. Versus to find the dimension of the null space of A, which does not have a fancy name, so that's the best you get. There is one vector, so we write the number 1. Remember, verifying our work here. If you add those two dimensions together, 4 plus 1 gives you 5, and if you look back at the original matrix, it had 5 columns in the original matrix, so we are on the right track there. Right? So what about this one? Instead of making you find everything, what if I just want you to find bits of one part to make sure you're learning definitions and the process? So example number 4 says this. Find a basis for the subspace spanned by the given vectors. What is the dimension of this subspace? All right, so you have to take what the definition says and break down what it's asking for. First of all, it says find a basis. So we know we're going to end up finding a set of vectors. It's defining this subspace as it being spanned by the given vectors. And if you remember, spanning is the definition of the linear combinations. Going back to the two definitions that we've learned, the only subspace we've talked about that involves the spanning or the linear combinations of vectors is the column space of A. So what we want to do is we want to find the columns, the basis of the column space here. That's good news because column space only requires echelon form, where null space requires reduced echelon form. So what I will need to do here is I'll need to write myself a matrix. Use the vectors that I provided here. So 1, -1, -2, 5, 2, -3, -1, 4, 0, -1, 3, 2, -1, 4, -7, 7, 3, -7, 6, -9. We don't need the 0 vector on the end because this is not a homogeneous matrix equation. So to put this in echelon form, let's see. We already have the 1. I got a little bit of work here to do. We're going to take R2 and just add R1. We're going to take row 3 and add 2 row 1s. And we're going to take row 4 and subtract 5 row 1s. So if I throw row 1 up here real quick, let's do a little bit of math here. So let's see, row 2 plus row 1, that would be 0, -1, -1, 3, -4. So then we are going to end up getting, where are we at here? We're going to take row 3 plus 2 row 1, so that's going to be 0, -1 plus 4 is 3, 3 plus 0 is 3, -7 minus 2 is -9, and then 6 plus 6 will be 12. Right? So then row 4 is going to end up being -5 row 1, so that's 0. 4 minus 10 is -6. 2 minus 0 is 2. 7 plus 5 is 12. And then we get -9 minus 15, which is -24. All right, so that's where we're at so far. So keep going. I actually notice a combination here. Let's make sure. Yeah, I think we're good there. It looks like that row 2 and row 3 are combinations of each other. So since that's the case, I know that the bottommost row, which for us is going to be row 3, that row is going to become all zeros. Now, since we really want a row of all zeros on the bottom, I'm going to go ahead along the way is after I do the multiples idea, I'm going to take row 3 and row 4 and interchange them. So what you should end up getting is this. 1, 2, 0, -1, 3, 0, -1, -1, 3, -4. I'm going to move, and actually, while I move row 4 up, let's go ahead and divide that all by 2 to make life easier. So I'm going to take the new row 3, and actually I'm going to do -1/2 to make it easier. So I'm taking this row 4, I'm moving it up, and I'm dividing everything by -2. So you should get 3, -1, -6, 12, and then I'll move the row of all zeros to the bottom. Now all I got to do is get rid of that 3 in the next, below the second pivot position, and I think we'll be on our way. So I'm going to take row 3, and I'm going to add 3 row 2s, because 3 plus -3 would be 0. The top rows remain the same, the top 2 rows really. So my next row, if I add 3 row 2s, you should get 0, 0. -1 minus 3 is -4. -6 plus 9 is 3. And then 12 minus 12 is 0. And then a row of all zeros on the bottom. In the end, that's as far as you need to go, because now we can simply identify our 3 pivot positions. And I don't need anything above them to be 0, so that's good. You've got your first 3 columns. So this is the x1, x2, x3 columns. So if I go back up, the first 3 columns of my problem should denote my basis of my column space. So the basis of the column space of A will equal the set of the first 3 vectors. 1, -1, -2, 5. 2, -3, -1, 4. And finally 0, -1, 3, 2. So there is your basis. And then it asks, what is the dimension? Well, the dimension of the column space of A, which is also equal to the rank of A. There are 3 vectors there, so that would be 3. And so I didn't make you find everything there. I'm seeing if you're learning the definitions and knowing what you're supposed to find. All right. And so the last thing I want to cover in this video is we're going to kind of extend what we covered in the last video. We did invertible matrix theorem, and that was the A through L combo. We're going to add 5 new things to that today that have to do with dimension and rank and column space and all that good stuff, null space, etc. So remember that the invertible matrix theorem says if A is a square matrix, then all of those statements were true or all of them were false. Remember, and going all the way back to part A, that says matrix A is an invertible matrix. So along with if A is invertible, all the other statements being true, the other 3 things that go together are this. If A is invertible, the columns of A must form a basis of Rn, which means that the column space of A must be equal to Rn, that dimension, which thus means that the rank of A must be n. And that means that every single vector of the original matrix must be in the column space, at least in the basis of it. Versus if A is an invertible matrix, that means the null space only has the 0 vector in it, and thus the dimension of the null space, as we talked about earlier, would just be 0, because you can only count non-zero vectors. And so if you're trying to put these back together, remember in the previous video 2.3, that's when we talked about the first 12 terms of the invertible matrix theorem. So I just have a couple more examples here under number 5 that kind of bring this back together. So let's see if we can answer these 2 questions to wrap this video up. Part A, if the rank of a 9x8 matrix A is 7, what is the dimension of the solution space of the matrix, the homogeneous matrix equation? So the first thing that jumps out to me here is that this last part, what it's asking for. It's asking for the dimension of the solution space of the homogeneous matrix equation. Going back to our definitions in this section, that is the definition of the dimension of the null space of A. We're trying to figure out what that is. The only other thing it told me in this problem is that the rank of this matrix, so the rank of A, is equal to 7. Now, earlier I talked about a way to verify if our dimensions are correct, and that was using the rank theorem that I showed y'all. So as a reminder, the rank theorem is going to say that the rank of A plus the dimension of the null space of A is equal to the number of columns, which is n. Now, if you use the problem in this case, they told us that the rank of A is 7. We do not know the dimension of the null space because that's what we're trying to find. And since they told us that the original matrix is a 9 by 8 matrix, I know that the original matrix has 8 columns. Doing some basic algebra here, you should be able to solve for the dimension of the null space of A. So subtract the 7 from both sides, and you have just found that the dimension of the null space must be 1. So there's only one vector in that subspace. It's basis. All right, part B of this kind of question says, if A is a 4 by 4 matrix and the transformation is 1-to-1, then what is the dimension of the null space? This is a pretty quick answer if you're starting to learn those steps of the invertible matrix theorem. So since it is a square matrix, we can use IMT or invertible matrix theorem. So by IMT, since A is a 1-to-1 matrix, or a 1-to-1 transformation, I should say, that's one of the true statements of the invertible matrix theorem. So that means every statement in IMT must be true. Well, if that's the case, of the 5 parts I added today, one of them talked about the dimension of the null space. The dimension of the null space of A, and I'm going to scroll back up. That is part Q of the invertible matrix theorem. Since I know one of the previous statements is true, then Q must be a true statement as well. So thus the dimension of the null space must be 0. And thus that probably means that only the 0 vector, also known as the trivial solution, will be part of the null space. So that ends my video on the combo section 2.8 and 2.9. That also wraps up the sections that we're going to cover in chapter 2. Starting in the next video, we're going to move into chapter 3, which is going to be our discussion on how determinants play a role in linear algebra.